Okay, so for this problem, what we're going to do is actually problem number 57, and we're going to calculate delta H, delta S, and delta G, and state whether or not the reaction is spontaneous. And I'll tell you why we're doing all three here when I do it. If the reaction is not spontaneous, would a change in temperature make it spontaneous? If so, should the temperature be raised or lowered? Okay. So we're going to do this first one. We'll do it on the next page, actually. But what we need to do on these problems, especially when you're not familiar with the calculations that much, write down the equation, make a table below the equation. Basically, we go down to the back of the book and we look up the values. Then you write out your calculations of reactants and products energies separately, and then you take the difference of them. And I just say that because if people try to write everything out at one time, a lot of times they make mistakes. And when they make mistakes, they can't track down where their mistake is. So if you just do it more systematically for a while, it usually works out better for you. Okay, so we're going to calculate all these values, and we'll calculate the temperature at which it becomes either spontaneous or non-spontaneous. Okay, so here it is. Let's go back to the appendix. We're going to look up N2O4 and NO2. And by writing a table underneath, all I really mean is you need your delta H, your delta G, and your S values. So you're actually going to look up, these problems take a long time. If I could draw this line straight, it wouldn't take as long. You're going to look up 6 values to do the calculations that you need. So for N2O4, you go to the appendix, and then you got to make sure you get the states right. So, like they have an N2O4 liquid, N2O4 gas, right? So, I'll pop back quickly. Are both in the gas state, right? So the values I'm going to use are N2O4 are those ones, and I'll just transfer them over so you don't have to watch me do the whole thing. And then NO2 is down here, I believe. And NO2 I've already highlighted. We used that in an earlier example. So I'll be using those values, and I'll just go transfer them over to the table now. So I've written the numbers over, and just so you know, I don't always write the units in the table if I can write them at the end, and it applies to everything in the line. Now for delta H of the reaction, I'm doing this one first because it's probably the easiest one to do. What I'm going to do is take the energy of the products and subtract the energy of the reactants. And like I said, it's easiest to write the calculation out, but then calculate these parts separately. So we're going to have 2 times 33.2. And really what this calculation is, it's 2 moles times 33.2 kilojoules per mole. So I can get the moles to cancel, but all I'm really going to do is write kilojoules at the end. So then it's going to be minus, and there's only one N2O4, so this is my product, this is my reactant, it's going to be 9.16, and this will be in units of kilojoules, and since it's times 1, I didn't bother to write the times 1 over here. So I'll get my delta H down here for that. Now, delta G and delta S are going to be done the same way. So it's going to be 51 point, oh sorry, I keep doing that, 2 times 51.3 minus 1 times 99.8. Units will be in kilojoules, and then I'll have my delta G down here, and then I'll do my delta S. And again, I'm kind of doing it in this order so I don't make transpositional errors when I'm reading the numbers off the table. I just try to keep them in the same order they are in the table. So now delta S, it's going to be 2 times 240.1, and then minus 304.4. Now, this is going to be in units of joules per Kelvin because I'm multiplying by the moles up here. So this is going to be joules per Kelvin. All right, and so what we'll go ahead and do is calculate all these values. And I should say I'm going to calculate them, and then you go ahead and calculate them. The video will just pop up here in a second. It'll have all the answers. Okay, so this is the values that I got. And then what we need to do next in answering the question, it says what is delta H, delta S, and delta G. So those are those values. And is the reaction spontaneous or non-spontaneous? Now, if that's the only question you're asked, this is why we're calculating all three. That's all you need to know. On the other hand, if you need to know, right, whether or not at what temperature the reaction becomes spontaneous or non-spontaneous, then what you need to do is you need to have delta H and delta S and use it like we did in this problem. Okay, so that's what we're going to do, and we know that the spontaneity is going to change. Right now it's non-spontaneous. So but just barely, actually. That's not a really big number. And then what we're going to do is calculate delta H divided by delta S and figure out what temperature it does become spontaneous. So this is going to be T is equal to delta H divided by delta S. Delta H is going to be 57.24. And I'm going to say times 10 to the third joules for every 175.8 joules per Kelvin. And the joules will cancel, and I should be in units of Kelvin. So this will be the temperature. And that comes out to be 325.6. Kelvin. And so in Celsius, if you want to know the temperature in Celsius, and I can't remember, it may have said in Celsius. Oh, should it be raised or lowered from 25? So it would be good to know that what this temperature is, right, in Celsius. So that'll be just minus 273.15. And that gives me 52.4. Okay, so what does that mean, right? Should it be raised or lowered? Well, this data is for the substance at 25. This is a higher temperature. Right now it's non-spontaneous because delta H is positive. So you need to raise the temperature to 52.4, and that's the temperature at which it will become spontaneous. So hopefully that made sense. We'll do another one. We go pick through the problem, and then we'll put it on the next slide and do it. Okay, so here's the next problem we're going to do, and what I'm going to just do is get a little bit set up for you. Again, use the tables. There's delta H, delta S, or delta G, and delta S. Or S, actually, not delta S. And I'm writing a little bit smaller because just with the one more value you have to look up, it's just going to take up a lot more space. So I'll pause it, and you go ahead and calculate the delta values from delta H, delta G, and S. Okay, so this is what I got for the first part of it anyways. Here's my delta H's and delta G and delta S. And I went through and actually, I didn't, watch this off camera, but I double check actually every time I do one of these. The common places to make mistakes are right here. Or when you're adding multiple things in the product, you forget parentheses, and then you end up adding when you should be subtracting a value. So I got these values. So what is it telling me? What it tells me is at 25 degrees Celsius that this process is non-spontaneous because delta G is positive. Now, it wants to know at what temperature it becomes spontaneous. And so we're going to go like this. We'll do T, again, is delta H over delta S. That comes out to be 712 degrees Kelvin. So in Celsius, that'll be 439, so basically 440 Kelvin, or 440 degrees Celsius. I just subtracted 273.15 from it. Okay, so basically then what you know is it's non-spontaneous at under these conditions. Oh, my mouse isn't showing up. It's non-spontaneous under the conditions specified by this calculation, which is 25 degrees Celsius, and then becomes spontaneous when you increase the temperature to 440 degrees Celsius. So that's basically how all these problems get done. You look up the values in the back of the table. The delta G and the delta S calculations are exactly the same as you learned for delta H, and we reviewed earlier in this chapter.